This is our seventh and final lesson in the simple harmonic motion topic. This is about damped and driven oscillators. And as we start thinking about damped or driven oscillators, we should really compare to just simple harmonic motion oscillators, where we have a few main ideas. One of them is that the acceleration is proportional to the displacement and in the opposite direction. And since force and acceleration are proportional, we can say the same thing for force. It's also proportional to displacement and in the opposite direction. We know that simple harmonic oscillators have a constant amplitude and a constant period, and we're always assuming that there's no frictional forces when we're dealing with simple harmonic motion. Now, as we get away from that, and we have some examples of when it's not simple harmonic, one of the things we can include is when there is friction. So if we go into what we call damping, is just a term for friction when we have an oscillator. Is just some frictional or resistive force that's opposing the motion of the oscillator. What this is going to do usually, it's going to decrease the amplitude, which we should expect with friction. One thing that's a little counterintuitive, though, is that it's going to increase the period. As it's going slower, it's going to take a little bit more time to go back and forth. Even with that decreased amplitude, we still get a slightly longer period. So it is going to take a little bit longer. Now, there are three types of damping. We have underdamped, overdamped, and critically damped. And you should be aware that these three exist. There's not really anything to calculate, but you should understand what each one of those means. When we have something that's underdamped, all that just means, and the under part means that there's just like not a lot of friction. So there's a minimal resistive force or just some amount of resistive force that just slows the oscillation down over time. It's going to keep oscillating. Eventually we get small changes to amplitude and period for each different oscillation. There's also what's called overdamped. Again, the over refers to the friction part. There's a lot of resistive force, and this is so much friction that it just doesn't even pass equilibrium, and it also takes a long time to reach equilibrium. Then there's also critically damped, which is when there's just the right amount of friction. We return to equilibrium as quickly as possible, and typically it's without oscillation. And I'll show you what some of those look like. A really good example is the shocks or springs in your car. You know, when you hit a bump, you don't want your car to be bouncing down the road for, however long. What you'd like to do is you'd like to return to normal driving without any bouncing. And so your springs or your shocks are designed to allow the car to return right to normal without taking too much time. Because if they were overdamped, you'd feel the bumps much more harshly. And so you want that ideal amount of friction. So I'm looking at a graph here of the amplitude versus time. So I'll put XO and negative XO, and then we'll have time here. Now, I'm going to just put some dotted lines here for reference so we can see where we're drawing. So that, if I have a simple harmonic oscillator, it's going to be the highest and lowest we get to. And let's go through one, two. We'll go through a full period. So there's T. You can actually even go past that a little bit more. Now, if we have a simple harmonic oscillator, let's say this starts from its amplitude. And we were drawing the path, or its motion over time. We would see something like that for simple harmonic. What we should notice is that the amplitude is staying the same. It doesn't decrease over time. And that's what we've been doing so far. So this I'm just going to say is simple harmonic motion for that blue line. Now if we have something that's underdamped is going to lose a little bit of energy each oscillation. So it might start at the same position, which is fine. But we should also keep in mind that what we set up above is that it's going to decrease the amplitude, but it's going to increase our period. So I am going to actually have to draw this a little bit further out, is that it's not going to reach these points at the same time. It's going to be a little bit extended past that, and it's also going to reach the bottom a little bit further beyond, and so its period is going to extend, and by the time I get through a full cycle, notice that I'm reaching this after the initial period from the simple harmonic motion oscillator. Okay, so that part's really important, is this period is not the same as before. and it's going to keep deviating as time goes on, and we can just stop at that point. Notice that also it reaches a maximum that's not quite as high anymore, so its amplitude is decreasing over time. And again, making sure to know that its period is getting longer. So this is what we'd call underdamped. So that's when there's a little bit of friction. Again, this is like any pendulum we could hang in the classroom. Eventually it would slow down and stop, and we would see that would also extend its period. Overdamped is when there's so much resistive force. Again, a lot of times this just doesn't even pass equilibrium. It might take a really long time to do that, so there's so much friction. It would be like running a pendulum maybe underwater or maybe in some really dense fluid, is that the pendulum would take a long time to reach equilibrium, and it might just not even reach it in the view that we're looking at. So this is overdamped. It's definitely not going to pass through equilibrium, but it's returning to equilibrium over a long period of time. Again, it just doesn't even oscillate. So that's the overdamps. And then the critically damps, this is the one where the critical is referring to, again, the ideal amount of friction to just return to equilibrium without actually oscillating. Now, that could look like a couple of things. Sometimes you'll see this as it just goes and just right to equilibrium and then just stops and stays right there. Again, this is like shocks in your car. Somewhat of an analogy is like those soft closed drawers in your kitchen. We don't want the silverware drawer to slam, and so that might be something that's critically damped, or like a really well-tuned screen door that closes quickly but doesn't slam into the door frame. So this is critically damped. There are some times that I've seen this where it can go past equilibrium just a little bit. It doesn't usually in most of these graphs, but you could see it go just down below, just barely. It sometimes can reach equilibrium faster if it goes below and comes right back. So it might need to just pass equilibrium a small amount. I'm going to leave that purple line, just knowing that it could be that black line sometimes. It can go past and still be critically damped. So those are the comparisons to simple harmonic and what we would have with our different amounts of damping. Driven oscillators are really just kind of the opposite. This is when you have, instead of frictional force, you have some driving force or some pushing force, some external force that's making the oscillation go in greater amplitude. So we get an increase in amplitude when our driving frequency, so how often we're pushing, matches what the natural frequency of the oscillator is. The natural frequency is just the frequency that something likes to vibrate at. If you're a musician, you know that there's a certain frequency for different strings with different tensions, or for different notes you play on different instruments. And so that frequency is always going to be the frequency that an object likes to vibrate at in order to oscillate. So this is a graph that you should be aware of. The IB really likes to include this in some of their questions. It's about how big our amplitude response is depending on different driving frequencies. So I mentioned here, this graph shows the resonant frequency. That's the frequency, if you're applying external forces, you get a really big response to amplitude. A good example of that is pushing someone on a swing. You have to push them at just the right time with just the right frequency. You don't want to push them too often. Sometimes they might be swinging back towards you and moving away from you. So the driving frequency that you want is the same frequency as how they're oscillating. Now, a swing is a good example because a person on a swing is just like a pendulum. You have somebody sitting on a swing, and so you pushing them every time that they come back and start to move forward again is matching the frequency of their oscillations. That's going to just give them a greater amplitude every time as they're going back and forth on that swing. Okay, and just to clarify, resonance as a term you should be aware of. You might even want to add that to your study guide. It's the tendency of a system to vibrate with large increases in amplitude, and again, at those certain driving frequencies, and that's really helping to explain what's happening here, is that at the right driving frequency, when it matches the resonant frequency, and a lot of times what you're going to see this labeled as is F with a subscript of 0. that's the resonant frequency labeling we'll use. That's when we're going to get the greatest amplitude of response. And then there are just a couple of other examples there. An opera singer in glass, tuning fork, which we'll get into in our next topic on sound waves. And another good example that people like to think about is when you get the reverberation in a car because somebody's rolled the windows down just to the right height. You get kind of a reverberation in the car, and that's due to the resonance. So I hope that helps clarify some of the either frictional or driving forces for an oscillator. And that is it for this lesson.